we are doing a tail to tip. This is our vectors, or these are our vectors. We have vector M. Vector M is 50 meters 45 degrees south of west, and the second vector, vector N, is 15 meters 30 degrees west of north, and vector O is 30 meters. Let me just change the color. Vector O is 30 meters 60 degrees north of east. Now the first thing that you have to you have to consider is the scale, and I already thought of a better scale for everyone. So for me, at least in the space that I'm working, it would be fitting to use this scale. Every 5 meters of my vector to be equivalent to 1 centimeter of my ruler. So let me just put some notes here. This is from my vector, and this one is in my ruler that I'm using. So since we're geometric method, we have to be very specific and accurate about how we illustrated the vector. Now, one of the things I've mentioned in class is that this actually vector addition. Oh, my dog is hugging me. No, down, Ajax. Vector addition commutes. So what this means is that if I take vector M, add vector N, and add vector O, I get the same result if I reverse the order, such that I have vector O plus vector N plus vector M. The order doesn't really matter. So it could be the same also if I start with vector N plus vector O plus vector M, and other possible combinations. Now, for the sake of this video, I'm simply going to be a good boy and just simply follow the order from M and O. Okay? So I also know that most of this vector will lie in the second and third quadrant based on the directions. So I will be wise enough to have my original very first Cartesian plane or XY plane, which defines my direction at this region over here. So I'm just going to do it here, maybe do it here, and then this is for my Y. It should be 0 degrees. All right. Okay, so this is my original XY or north, south, east, west direction, and it will come into play important role later. So this would be my north, my south, my east, and west. And basically these are arbitrary directions which I have freedom on where I will put my north and east, for example. Okay, now let's start with the first vector. First vector is vector M. It's 45 degrees south of west, so that means to say we set our 0 degrees from west going south. So we call in our old protractor here, and then let me just move this downward. Alright, so the direction again is south of west, so west should have the 0 degrees, so I will reorient my protractor like this, such that 0, I'm hoping you can see, 0 degrees is now on the west, and I'm going to move south, and south is here, so the angle should go towards this direction from here to here. So I'm going to use red for the first vector, and 45 degrees is somewhere over here, and so that is where 45 degrees is. So for the first vector, it's 50 meters, and according to my scale, I simply have to use or represent it by drawing 10 centimeters. So my ruler has to pass through the point that I identified earlier and at the origin of my XY plane, which denotes my direction. So like this. Okay, it's quite challenging to move this virtual ruler thing. Alright, yep, that's it. So that's my 0. So I'm going to draw 10 centimeters to represent vector M. Alright, like that. So let me do it. Oh, no, I cannot tolerate that. So, oh, no. Alright, so this is my vector M. Now for the second vector, we are dealing with tail to tip, right? So the tip of the second vector will be placed on the tail of the first vector. So we define again our new XY plane. I'll denote it by the dotted line so that it won't be confused with my original XY plane. and use black for that. Okay, here. Okay, and also I'm hoping this is okay, 0. Good. Okay, now another thing that we have to be mindful is the consistency in our directions. If this is how we oriented our north, south, east, west, it must be the same all throughout the like the Cartesian plane, which defines our directions. So let me just define this again by saying that this is my north, this is my south, this is my east, and this is my west direction. And again, guys, you have to be very consistent about that. So my second vector is 30 degrees west of north. So it starts from north going west. So again, your 0 degrees on your protractor should be situated north. So I'm going to pull this over here. Okay, and measure it well. And my north should have the 0 degrees, so I will rotate it in this manner. Good. So at this point, you're now seeing that this here is my north direction. It has the 0 degrees. Now I have to move to west. So that means to say I have to move to west and I have to measure 30 degrees. Okay, now 30 degrees is quite easy to find. I'm going to use blue for that. This is this point over here. That's my 30 degrees. Or let me just do it better. 30. Here, along this point here. Oh, it's shifted a little bit, so let's make it very exact. 30, yeah, that's good. So that small dot there represents my 30 degrees, and my vector, which is 15 meters, can simply be represented by 3 centimeters. So let's do the same thing. So set that at 0 degrees, but you have to remember that it must also pass through the point which indicates your direction, and you have to be very careful about it. Okay, wait, no, it's not really passing through the origin, so let me just redo that one and a little bit change on the direction. So I'm hoping this is how you really do your work, because geometric approach in adding vector needs to be very precise. Okay, and oh my god, yeah, 3 cm. So from my origin, oh, it shifted a little bit. Okay, that works. Okay, so that's my vector n. Put vector n and a little hat to indicate that it's a vector. Alright, so we're now down to the third vector. So again, we go back to what we did earlier. We define a new xy plane, or the Cartesian plane, which defines our directions. So this will be it. And also for the y should be this point. So it should be on the very tip of the vector. Alright, and as I've said, consistency is key here, guys. So this should be north still, this should also be south, and this should be east and west. Never interchange your directions, so you stick with what you decided in the first place. Consistency. Alright, so the third vector is vector O. So it's 30 meters from north of east, 60 degrees north of east. So meaning, just like what we did earlier, you start from east going north and measure 60 degrees. And 30 meters, if we're going to use our scale, is just 6 centimeters. So I'm going to get my protractor again, and where do I set the 0? I should set my 0 to east. So east is right here, so I'm going to tilt my protractor, like this. The 0 should be on east, and I should move to north, measuring 60 degrees, right? So my north direction is right here, and this is east, so 0 should be on the east going north. And I'm going to find 60 degrees. 60 degrees, I'm going to use a different color for this one, maybe violet. Yep, 60 degrees is right over here, along that. Okay, so we're going to represent a third vector, and as we have seen earlier, it's just 6 centimeters because of the scale that we use. So the same thing, the line that we are going to draw should pass through the origin of our axis, and it must also pass through the point which denotes our direction. So right here, where is it? Okay, 0 is right here. Okay, it passes through that point. Good. Up until 6. Maybe let me just move this a little bit just to be very precise. Alright, it's really 6. I'm hoping you can see it. So this right here is our vector O. Okay, so that's our vector O, and it's the moment of truth. So we go back to our very first Cartesian plane, which defines our direction, this one. And I said it played a significant role. This is it. So from there, we just find a better color that could be, maybe green. Yeah, I like green. So from here, guys, so this will be something that I have to measure. So that's 0. I have to measure the length from that up until the end of the tip of the last vector which I added. So let me just get this right by tilting my ruler. Okay, I think this is good, but I would just like to be very precise. Right, like that. So let's do the measuring. So that's 0, and it's 5.6. Okay, so according to my calculation, this is the resultant vector r. Alright, it's 5.6, right? So I'm going to put it here that the magnitude is equal to 5.6 centimeters. And I'm going to multiply it by my scale factor. Every 1 centimeters is equal to 5 meters. So you can calculate that one. Let me just grab my calculator. I know it's very easy to calculate, but I just have to do it on the calculator for trust issues, because of trust issues. So after calculating that one, I got 28 centimeters. Oh no, 28 meters. 28 meters. That means that's how long that vector should be. I'm hoping we did have the same answer. And on this one over here, I'm going to get the direction. So I have 2 ways of getting the direction, and I want you to listen to this one. The first one is the easy one. The easy one is like this. So let me just tilt this for easier reading. Alright. So notice what I did here is I'm going to measure this angle from north going towards the green one, which is my resultant vector. And as you can see, of course, this is 0, this is 10, and so on. So this angle over here, if you can read what this is, this, I'm going to call this theta 1, is actually 83 degrees. Alright, so I'm going to write it here. The direction is 83 degrees. And let's go back. We set our 0 from at north going west, so that should be west of north, right? West of north. But there's another angle, which is this angle over here, which is from your math, it's just the complement. Okay, this one. Okay, this small angle here, if that's the other one is theta 1, this small angle is theta 2. And that is just 5, I'm going to show what I'm talking about, 5, 6, 7, maybe 7 degrees. So I'm hoping we did have the same answers. So the second angle is just 7 degrees, and this will just be reversed north of west. Alright, I'm hoping we did have the same answers, or at least close to these answers. Bye bye.